Alright, physics, we're back at it. Um, we didn't, like, leave off here. I guess we kind of did, like, before the break. Not here, right? It was, related to here. Over here. Spring potential energy, right? It was kind of like the last thing that we had talked about. And I had said that spring potential energy was almost the last thing. There's one and a half loose ends to tie up here with energy. It's related to energy. Energy is your ability to do stuff. It's like the currency of the universe. If you have energy, you're allowed to do things. If you don't have energy, you're not allowed to do things. Depending on how much energy you have, you can do more or less things. Those things actually have a definition, and that is the part of the last thing that we'll talk about here before the midterm. So related to work, or sure, related to energy is this concept of, and that pen size is just terrible. Let's change that. This concept of work, right? So work and energy are tightly related, right? Energy could also be defined as the ability to do work, and work is loosely defined as the process, the act of changing the energy of an object. Now, linguistically, these are not great definitions because they just like recur into each other. It's a cycle. It's not a good thing to do, but in physics, it makes sense because work and energy are functionally the same thing, right? There's actually an entire thing. It's the work-energy theorem, and it says that work is defined literally, like mathematically. Work is defined as the change in energy of an object. So if I were to take my phone and lift it from here to here, I've done work on it. Because by lifting it higher off the ground, I'm giving it more gravitational potential energy. So I'm changing the energy of my object. I'm doing work on it, right? This equation, by the way, W equals delta E, is one of the last equations on that last page of your reference table. Usually when you look at work, we have a slightly different definition. We call it force times distance, F times D. You apply a force to an object, so in the case of my phone again, right? Applying a force upwards, and I'm moving at a distance upwards, right? So apply a force in order to move an object a certain distance. You're technically not doing work on something if you're holding it in place, or if it doesn't move. So like pushing against the wall, right, is not technically work because the wall isn't moving. The wall's not going anywhere. It's applying a force back, right? Equal and opposite. You have Newton's laws. But even though you're applying a force to the wall, you're not moving it across any distance. You're not doing any work, right? So a lot of like, I think it's isometric exercises, right, where you kind of like hold an object in place. Technically, not work, even though you are you're resisting something. You're resisting motion. But work is defined as changing an object's energy or applying a force to move an object a certain distance, right? A very typical work question might be, you push a 5-kilogram box using a 30 Newton force down the hall, using a 30 Newton force, 20 meters down the hall. Right? So it's a 5-kilogram box. You use a 30 Newton force to push it 20 meters down the hall. Right? How much work did you do? How much work did you do on the box? Right? Fairly straightforward. Pretty, seems easy enough. Work equals force times distance. The only thing to be careful of, this question gave us too much information. I have a 30 Newton force. I have a 20 meter distance. This information, not useful. I didn't need the mass for anything. Like, it's there. Maybe I would have needed it for something else, but not here. Right? Work equals force times distance, which means it's 30 newtons times 20 meters, which means that we did 600 joules of work. Work is the same as energy. It has the same units as energy. So work, force times distance, measured in joules. So 600 joules, there it is. Right? Alternatively, right? This is one version of how you might be asked about work. Hello, please. I don't know why it doesn't want to move. Oh, okay. It all moved at once. Cool, great. Alternatively, you lift a 5 kilogram box 1 meter off the ground. How much work did you do? Right? How much work did you do? Well, I would like to do work equals force times distance. However, I don't know the force. The only information I have is 5 kilograms and 1 meter. That's a mass and a distance. That's not super helpful. However, remember that it also equals the change in energy. Right? If I'm lifting a box, if I'm lifting something off the ground, then I am changing its energy. I'm changing its potential energy, which means that the work that I've done is going to be equal to the change in potential energy, or m times g times h. I know the mass is 5 kilograms. I know that the acceleration due to gravity is 9.81 meters per second squared, and I know that the height is 1 meter. And according to math, which is to say, according to my phone calculator, 9.81 times 5, this equals 49.05 joules of energy, which means I did 49.05 joules of work. Really 49. 49 joules is probably more appropriate here. But it's another way that you might be asked about work without having like a force and a distance. Right? Related to this concept of doing work, the rate at which you do work, how quickly you can do work, is power. Right? How quickly, or the rate at which work is done. Right? So it's how fast can you do work. If you do work kind of quick, you have a little bit of power. If you do work very quickly, you generate a lot of power. Power is equal to the amount of work that you've done divided by time. There are expansions of this. This is the final equation on that reference table. It also equals F times D over T, because we know that work is force times distance. And if I combine distance divided by time, it also equals F times V. Right? You have all these different versions. It just depends on what information you were given. Now, again, I will say it is fairly obvious that you will be using a power equation because the question will ask about power. Right? If you have numbers, it's very straightforward. Well, sometimes you'll be asked a question like, 2 students carry identical suitcases up the same set of stairs. If student A goes twice as fast as student B, which student generates more power, right? So this is like a kind of a I call them like real physics questions, because there's no numbers. It's just like, do you know kind of what's happening, right? Well, if we want to worry about generating power, then we need to worry about how much work did these students do and how much time did it take these students. They're carrying identical suitcases up the same set of stairs. So they're going to do the same amount of work. They're going to apply the same amount of force over the same distance. They're going to change the energy the same amount. They're lifting them up a certain staircase. So the force is the same. The time is the only difference. Student A is twice as fast as student B, which means student A is going to generate twice as much power as student B. Because student A's time is smaller, right? This time is smaller, the fraction is going to end up being bigger. It'll be twice as big, right? Now the units for power are watts. You might think horsepower. Technically, horsepower is a unit of power. It's like an antique unit. It's not misleading, right? So car engines still love to be measured in horsepower. If your car engine has a horsepower of, it's like 350 horsepower, that doesn't literally mean it's the same as 350 horses dragging you. Horsepower was like defined as how much work can a horse do in a certain amount of time? Like how much of a field could it plow in a certain amount of time? Something like that. Again, it's wildly out of date, but we still use it for cars because car enthusiasts, I guess. But if you do need units, we actually use watts. So like electrical power, right, is measured in watts. A 50-watt bulb is not as powerful as a 100-watt bulb. So watts. So if you have to actually calculate, the units that you would use are watts, which is abbreviated with just a capital W, like it would be on a light bulb. Right? Now, I'm going to post some questions on work and power and kind of like generically energy. I'm going to post those questions on my CBA. Finish those questions, submit them online. We'll talk about them during the next class. I'll kind of go through them quickly at the beginning of the video. And then, we'll actually start another lab on sometime next week, early next week, because late next week, remember, Thursday or Friday of next week, there will be an online test. It'll be a baby midterm, right? It's going to be literally half of it, because it'll be, I'm going to time it out. It's going to be half an hour, which is half of your midterm, right? Your midterm's an hour long. So kind of try to use that timing, use that as a gauge for like, okay, I know how to do this, I know how to do this. I wasn't really sure on this. Maybe I should ask some more questions. Maybe I should, try to practice that more, look at that again. But give that a shot, all right? Give it's work, power, and energy. So it's a little bit of everything because they're all related. But give those a shot. I'll go over those next time. Until then, until I see you in class or until the next video, take care of yourselves. Be good, kids.